Enhancement MOSFETs are also often used as switches, and they're used, what I mean by that is that they're used to turn a circuit on or off, allow current to go through a circuit, or allow current to, or force current to stop going through the circuit. But first of all, let's just look at a simple switch circuit, and then look at where MOSFETs might be used instead as a digital control over, or electronic control over the switch. If we've got a voltage source of some kind here that's supplying the current to, let's say it's an LED, a really powerful LED, or maybe an array of LEDs, and this circuit here is drawing 1 amp of current. So we have this circuit, and if this was, say, like a flashlight or something like that, we might have some kind of physical switch that we could open or close to allow current to go through the LED to light it up, or to open up the switch and stop current from going through the LED to turn it off. Now, this would be great, this is fine if you want a mechanical switch, but what about if you want to have some kind of digital control over whether that LED is lit or not? So you have some kind of digital control, either a microcontroller or an FPGA or CPLD or something like that. And we got this output connection here. And, you know, if you might think that you could have this output connection, so it's like a 5-volt output from, say, an Arduino or something like that, connected up to this LED and then connected to ground. And if you put a 5-volt here, 5-volt output on the pin here, the LED will turn on. If you put a 0-volt here, the LED will not turn on. But if this was the same LED or array of LEDs as up on this example, that needs 1 amp to go through it, that's not going to work, because many digital circuits, microcontrollers, FPGAs, have a limited amount of current that they can output. For example, on an Arduino, I believe it's about 40 milliamps that they can output on one of their digital pins. So there's no way we would be able to drive 1 amp through this LED. So instead of doing that, we can still have the digital control, but that signal doesn't go directly to the LED. That signal goes to a FET, acting as a switch. Here's my FET, and then the connection up here is to the LED, current limiting resistor, and then the voltage source, let's say 5 volts again. And LED here, so we can have 1 amp going through here. The FETs are going to, well, you pick a FET that allows 1 amp to go through, and the output of this digital circuitry is either going to be 5 volts or 0 volts. So if it's 5 volts, and as long as 5 volts is greater than the threshold voltage for this FET, so let's go 5 volts is greater than the threshold voltage of this FET, then we will have current going through this circuit. And if it's 0 volts, so ID, we'll have some ID. If it's 0 volts, then we'll have ID of equal to 0. And for any FET, you just have to have a voltage greater than that threshold voltage that will create a channel between the drain and the source, and then you'll be able to have current flowing through this circuit, and that LED would turn on. We're going to come back to that point in a minute, because that's actually not enough. That's not enough information. There's not enough. The condition is not quite enough to satisfy making this FET a good switch. But before we get into that, let's look at BJTs as switches versus FETs as switches, because I could do the same thing here. I could put a BJT in the circuit, and it was going to work pretty much the same way. Maybe I'd need a current limiting resistor here if it was a BJT, so I'd need a base resistor. But I could use a BJT in the circuit as well. So I just want to quickly point out 3 reasons that FETs can work better as switches than BJTs. And the first reason is that FETs are more resistant to thermal runaway. And I'll just show you what that means in a second. So, thermal runaway. And thermal runaway exists in all sorts of things, and it's basically when you've got a positive feedback loop where the heating up of some kind of device causes some other characteristic to change, which causes a thing to heat up even more, and so you get this positive feedback loop, and eventually the thermal runaway, that device is going to burn up, burn out, disappear, go away, blow up, whatever. For BJTs, the thermal runaway is exhibited in this way. If you've got a circuit where the collector current is increasing steadily, and what's going to happen if the collector current increases is the temperature is going to increase. Now, usually you're going, as long as this IC, this collector current, is less than the rated current for that BJT, the BJT is going to be able to dissipate that that extra heat, and so the temperature of the BJT won't rise. But if it's unable to dissipate that heat, it's going to the temperature is going to increase, and what's going to happen is that's going to cause the base emitter junction voltage, the voltage across the base emitter junction, to increase. And now if the base emitter voltage increases, that results in an increase in the IC, which then will result in an increase in the temperature, an increase in the base emitter voltage, and you've got this positive feedback loop. And this is an example of thermal runaway. For a FET has some protection against thermal runaway. If the drain current increases, and so you've got a high drain current, and as long as that drain current is less than the rated drain current, then the FET will be able to dissipate the heat. But if it's not able to dissipate the heat, the temperature is going to go up of the FET. The temperature of the FET is going to go up. But what's going to happen is the drain source resistance is going to increase, and that's going to result in a decrease in the drain current. So you have a negative feedback loop going on. Increase in the ID results in an increase in temperature, but the drain source resistance increases, so the drain current will drop. Negative feedback protecting from thermal runaway. The second thing that's sort of related to this thermal runaway is that FETs can be placed in parallel more easily. If you place two BJTs in parallel, so let's say we got these two BJTs here in parallel. Both of these BJTs are acting as switches. We got the base of both of them is connected to whatever the control circuitry is, and the emitter is connected to ground over here, and the two collectors are connected to whatever the load is. And the idea here is that you've got two BJTs that can't sink this much current, whatever this current is. You put in two in parallel, half of that current will go through one BJT, half will go to the other BJT, and they won't be rating, or they won't be exceeding their rated current. But neither one of these, well, these two BJTs probably are not going to be matched perfectly, and so what that means is one of them is going to have a higher base emitter voltage to forward bias that base emitter voltage. Might be a slight difference, but what will happen is one of those, whichever one has the higher base emitter voltage, is going to have the higher collector current go through it, and so it's going to start hogging current. So let's say it's this one that starts hogging current, and as it hogs current, it has the potential to increase in temperature, and you get this positive feedback loop going on again with the thermal runaway. This BJT here is going to eventually burn out, and then the only path for the current then will be through the second BJT here, and it also will burn out because it wasn't rated for this collector current, whatever it is. However, if you've got two FETs that are put in parallel, so just imagine that I've got two FETs in parallel here, same idea, they're there to share the current. The FET with the lower RDS is going to get more of the current, but then its temperature is going to go up, which will cause an increase in RDS. And so you're going to get a balancing effect. Eventually those two FETs are going to balance out, and they'll have approximately the same drain source resistance, so they will share the current equally, and there will not be an imbalance of current. The third reason that FETs work better as switches, and this is only in high frequency circuits where you're trying to switch the FETs on and off really quickly, so like in digital circuits, FETs work better because they switch on and off faster. BJTs are just can't keep up with FETs in terms of switching speed. So those are the three reasons that FETs are better switches than BJTs. So remember back in the beginning where I said that as long as this gate source, as long as this voltage applied here at the gate, so that's ultimately the gate source voltage is greater than the threshold voltage, then you get ID. You'll have current flowing through the drain here, and if the gate source voltage was less than the threshold voltage, then what you'd have is ID equal to 0, well, ID something greater than 0. If your gate source voltage is less than VT, then ID is going to be equal to 0. So this is true. This would allow the current to start, VGS greater than VT would allow the current to flow between the drain and the source. But what we want to do is make sure that the drain source voltage is as low as possible. And the reason that we want that drain source voltage to be as low as possible is because of power dissipation. The power in the circuit is going to be equal to current times the voltage drop across the resistor, plus that drain current, same drain current, times the voltage drop across the LED, plus that drain current times the voltage drop between the drain and the source. So this here, that's the power that's useful. That's the stuff that's turning the electrical energy into light energy. This would be power dissipated by the transistor. Not so useful. That would just be dissipated as heat. And same with this, but let's just ignore that for now. We're going to focus on just the transistor. So when VGS is less than VT, we'll have no drain current going through it. So ID will be 0, so the power dissipated by this part of the circuit will be 0. Actually, power, the whole thing is going to be 0. But when VGS is greater than VT, we will have some drain current. And ideally, if VDS is equal to 0, we'll have drain current times 0 voltage would give us 0 power. We won't have 0 VDS, but we can design it to have as low a VDS as possible, or at least a low VDS. And the way that we do that is we make sure that we're biased in the ohmic region. Remember the relationship that we have between drain current and drain source voltage. For some VGS, and so we'll have several of these curves, but for some VGS value, you see the lower we get our VDS, the closer, or if we have a low VDS, we're going to be in the ohmic region. So this side of the dot approximately is the ohmic region. This side would be the saturation region. In the ohmic region, the FET acts pretty much as a resistor, and the slope of that line is equal to 1 over the slope of that line, or the RDS is equal to 1 over the slope of that line. So we're acting sort of like a resistor there. And if you look on the data sheet for a FET, it's going to give you the RDS, and it's going to give you the RDS for excuse me, for a particular VGS value. So this VGS must be greater than the threshold voltage, and it's going to give you that, and that RDS is going to be true for some particular ID value. So it's going to say at this particular point there, and it's going to call that, we might call it ID on, that'd be a typical name for it. At a particular ID on and a particular VGS on, it's going to say that your resistance between the drain and the source is going to be some particular value. And as an example of something I've just pulled off of DigiKey, we've got some particular N-channel MOSFET transistor, and you see here RDS on is 1.15 ohms at some value of VGS of 10 volts and at a value of ID of 2.5 amps. So if, for example, you were given a circuit that looked like this one, and you were given the task of verifying that it's a good circuit, the first thing that you would do is make sure that your VGS is greater than your VT when you're trying to turn it on. The second thing that you would do is to verify that it's operating in the ohmic region. So to verify that it is operating in the ohmic region, First thing we're going to do is we're going to pick, well, what we're going to do is we're going to have to pick a transistor, a FET, where the VGS that we use is the VGS on for that's from the data sheet. The gate source voltage, so your control voltage is equal to the VGS on data defined in data sheet. I mean, this is not a necessary example, but it's going to help your verification. It's going to make the verification that you're in the ohmic region easier. The second thing you're going to do is calculate saturation drain current. So this ID sat is when you assume that the drain source voltage is 0. So let's do that. Let's say for this, let's assume for this FET VT is equal to 2.5 volts, and the VGS of 5 volts is VGS on. So this circuit and this graph correspond to each other. And the next thing we're going to do is figure out ID sat. So in the circuit there, ID sat, we're going to need a couple more pieces of information. It's going to be equal to the source voltage here, let's say it's 5 volts. We're going to have to subtract this voltage drop across the diode. Let's say the forward voltage drop across the diode is 2 volts. VDS is 0, so we don't worry about that. We're connected straight to ground at this point. And our resistance here, let's say the resistance up here was just a really small 3 ohms because I need lots of current going through here. So 5 volts minus 2 volts over 3 ohms. My ID sat, let's say, is 1 amp. And I haven't defined an ID on for this, just say to make this work. Let's say the ID on was equal to 1.3 amps. So, just in summary, what we've got so far, we've got this particular circuit here where we have 1 amp going through, actually no, we don't know that yet. For this particular circuit here, we've got a FET that has a threshold voltage of 2.5 volts, and for a VGS on of 5 volts, we have an ID on of 1.3 amps. And in the particular circuit that we have, we calculated that the ID sat is going to be 1 amp. And the third thing we do when we're verifying the ohmic region is check if the ID sat is less than ID on, you're in the ohmic region. And the reason that's true is, here's my ID on of 1.3 amps. My ID sat is somewhere down here. So ID sat is when your ID when VDS is equal to 0. Well, my actual ID is going to be something less than 1 amp. So the reason that we know that we are in the ohmic region is because we can create the load line for the circuit, and the ID sat is one point on the load line, so it's right here where we've got about 1 amp. ID is 1 amp, VDS is 0. The other extreme is when VDS is equal to VDD, or 5 volts, so somewhere over here, say. And our load line would be just the straight line between these two, and the intersection of the load line with our VGS value shows that we are in the linear region. So this will be our actual operating point, and that operating point is in the linear region. So if for a VGS equal to VGS on, if your ID sat is less than ID on, then you are in the ohmic region, and for this particular example it checks out. So let's do one more example just to wrap up and to step through everything from the beginning again. So you're given this particular circuit where you have digital control that's either 4.5 volts or 0 volts connected to controlling the gate of this 2N7000 FET. And we've got a load of 1 kilo ohm that's being powered by 20 volts. And this characteristics for the 2N7000 is that at some particular value, VGS on of 4.5 volts, you will get an ID and at an ID on of 75 milliamps. Your RDS on will be 6 ohms. So is this a good circuit? In other words, are we operating in the ohmic region? Well, first thing to do is check out the ID sat. Well, the first thing to do is make your digital control the same as VGS on. In this case, that's true already. So the second thing then to do will be calculate the ID sat, which is 20 volts over 1 kilo ohm. ID sat is when we assume that the drain source voltage here is 0. That works out to 20 milliamps. 20 milliamps ID sat is less than ID on. Therefore, we are operating in the ohmic region. Just write that out. ID sat is less than ID on. Therefore, we are in the ohmic region. And just to redo the graph to show you what kind of how we're operating here, we've got for some our VDS versus ID curve for some VGS on. So this is at VGS of 4.5 volts, and VDS and ID. At some value of 75 milliamps is ID on, so that's sort of our operating point, and we're going to have an RDS equal to 6 ohms. So the inverse of the slope at that point will give us 6 ohms, and our actual operating point is somewhere way down here. We're actually at 20 milliamps here, and that would be one extreme of the load line for this circuit, and the other extreme of the load line for this circuit would be down here at ID of 0 and VDS of 20 volts. We draw the load line, and this point right here is our actual operating point, and graphically we can see that we are definitely in the ohmic region. And what is our actual VDS? Well, first of all, we can calculate what our actual ID is. ID sat was 20 milliamps, so ID, what is the actual ID? Well, it's going to be 20 volts applied across this 1 kilo ohm plus this 6 ohms. 20 volts divided by 1,000 ohms plus 6 ohms. And that works out to 19.9 milliamps. So if ID is 19.9 milliamps, VDS will be 19.9 milliamps times 6 ohms. Voltage equals current times resistance, and in this case it works out to 0.12 volts. So that point there would be 0.12 volts for VDS. And we can even figure out what the power dissipated by this transistor is going to be. Power dissipated by the FET will be 0.12 volts times 0.0199 amps. Works out to 2.4 milliwatts. Very low power dissipation for the FET compared to the load, that 1K resistor. Voltage, let's do I squared R. So I squared 19.9 milliamps squared times 1,000 works out to 396 milliwatts. So many more times the power dissipated in the load than by the FET, and that's exactly what you want. Alright, I hope you learned a little bit about power FETs, or using FETs as switches in circuits, and I'll see you in the next